Okay, so I wanted to go over a couple questions from the self-test that somebody asked me about, which were 1, 2, and 6. All right, so question number 1 is an exponent rules question. It says simplify this. So if I was simplifying this, I guess I would say this is 81 m to the 6, and when you square root something, you're raising it to the 1/2 power times 3m. And actually, what I could do, if it's a negative exponent, I can put it on the bottom. So this is 3mn to the 3rd power. And so then you have to, when you raise a power to a power, it's multiplying, and you have to distribute the exponent into all the different factors inside the parentheses. So I need 81 to the 1/2 power, which is the square root of 81, which is 9. I need m to the 6 divided by 2 is 3. Then on the bottom, I have 3 to the 3rd power, which is 27. M to the 1 times 3, which is m to the 3rd. N to the 1 times 3, which is n to the 3rd. The m to the 3's are going to cancel. 9 over 27 cancels to 1 over 3. And I get 1 over 3n to the 3rd. Let's see. For simplifying this complex fraction fully, I think what I would do is always look for one step that gets rid of the fractions within the fractions. And if I multiply the bottom expression by a, then that's going to do that for me. And I can do that as long as I'm multiplying with something that doesn't change the value of the expression itself. It just is sort of like it changed the way it looks. And if I multiply by top and bottom to an expression, I'm effectually multiplying by 1, and by multiplying by 1 doesn't change the value of anything. So that's why it's a legal maneuver. If I do that, I get a squared minus 2a divided by 4 minus a squared, which is a nice step in the right direction. And then I'm going to start factoring now because I don't have any factors within fractions within fractions. I just have one numerator, one denominator. I'm going to factor out an a from the top, and I get a times a minus 2. And on the bottom, this is a difference between squares, so I can call this 2 minus a times 2 plus a. And at first glance, it might not look like I have anything in common, but if you think of what you have when you have a minus 2 over 2 minus a, or a minus anything over that thing minus that over, if you have the same expression, there's just a minus sign in between them, and the terms are reversed. If you plug in a number, like let's say 3 minus 2 over 2 minus 3 is going to be 1 over negative 1. If I plug in a number like 10 minus 2 over 2 minus 10 is going to be 8 over negative 8. I don't got time to keep on going for that, but hopefully I've convinced you that you can cancel these factors, but they don't just cancel to 1, they cancel to negative 1. So I have to put in a negative sign there. So then I get negative a divided by 2 plus a. And for problem number 6, are these functions inverses? Well, one way to do it would be to just derive the inverse, but I'm going to take the alternate approach, which is to plug one inside the other. And if it simplifies to just x, then I'm good, and I don't have to, I know that they're inverses. And if it doesn't, well, I should take that back. If it simplifies to just x, I should plug the other inside of it. If they do simplify to x, they're inverses, and if they do not, then they are not. So in this case, this squared thing is going to cancel out the square root. So I get 3 times x plus 2 divided by 3 minus 2. Then the 3's are going to cancel. Then I get x plus 2 minus 2, which equals x. So that looks promising. And just to be thorough, I'm going to plug f into g also. So I get g of x is equal to blank plus 2 divided by 3. inside the blank goes 3x squared minus 2. I don't really need these parentheses at this point. I notice that the minus 2 and the plus 2 are going to cancel. Then I'm going to have the square root of 3x squared divided by 3. The 3's are going to cancel. I get the square root of x squared, and that cancels to x. And so my answer would be yes, because f of g of x equals g of f of x equals x. The functions are inverses. And that's my show. Hope you enjoyed. There we go. That's my show.